What is up, most distinguished patrons of this channel? So for today's video, we're going to dive into the world of AC TIG welder settings, and we're going to come to an understanding of what they do, when to use them, and everything to do with that. So with that said, let's get into it. So it goes without saying that if you've been around a AC TIG welder, especially some of the higher end ones, you've seen that they have a ton of settings and you probably don't understand what a lot of them do. Even a lot of advanced AC TIG welders, guys that weld aluminum a fair amount, don't even understand what the settings all do and when to use some and not the others. You get the idea. And that's why I had to dedicate a whole video on this so that everyone out there that's watching this How to TIG Weld Aluminum series all are on the same page. Like, you have to understand what these do so that you can understand when you need them, when you don't, if you need them at all. And I'm not joking about it. Like, it can be very confusing. And especially if you have a more advanced AC TIG welder, like, what's the point of having all the features if you don't even know what they do and you don't screw around with them enough, and then you try and experiment and have undesirable results? And that's the point of this video. I'm trying to get all of you guys onto the same page as where I am on understanding this stuff. So the first thing we're going to do, because I got a list here, had to make a big list, and I got more that we're going to talk about besides what's on here. But we're going to start out with the most important thing you need to understand about settings, and that is amperage. Probably the biggest thing that I've learned since I've become very competent at aluminum welding with TIG is how understated amperage actually is. Like, when I was looking for my first AC TIG welder, which happened to be a Lincoln TIG 200 many years ago when they first came out, the biggest selling point that everyone told me was features like adjustable AC balance and frequency and all of that, when the truth is, when it comes to welding aluminum, the number one most important setting is amperage. And aka, you need a big enough machine with enough amperage to do what you want to do. And case in point, 1/8 inch aluminum like I have back here takes upwards of 200 amps to weld. And I know that sounds absurd for that thin a material, but the material dissipates heat so well that you really need a lot of amperage. Directly correlating with the amperage is what's called duty cycle, and it's something you really got to watch out for. With aluminum, because it takes so much heat input to actually weld it, you tend to run a lot higher on a duty cycle than you normally would. A great example would be, I can weld 1/4 inch or 6.4 mil steel at about 140, 150 amps with any kind of DC TIG welder, no problem. Well, with aluminum, 1/4 inch, you're going to need a 200 amps, and you're going to be flat-footed at that, and you're probably not going to have enough heat input. And this here is a pretty typical duty cycle of a 200 amp class machine. If you look there on the lower right where it says 25% at 205 amps, that machine on 240 volts can only operate for 2.5 minutes out of 10 at 205 amps, its max output. So if you're welding anything over 3.2 millimeter thick or 1/8 inch aluminum, and you're doing things like fillet welds, you're going to need all of that amperage, all 200 amps of it, at least at the start of the weld. And if you're welding anything thicker than that 1/8 inch, then you're definitely going to be full pedal, and you're probably going to end up hitting the duty cycle of the machine pretty quickly. And honestly, I think that's why they include a 17 size torch with most of these 200 amp TIG machines. And the reason's simple, is that the torch will start melting and smoking, and it kind of gives you a warning, hey, let the torch cool off. Well, during the time the torch is cooling off, the welder is also cooling off, which allows you not to hit thermal overload. Now, I'll be honest, that TIG 200 that I started with, I never actually hit the duty cycle on it, and I welded a ton, but that was an okay piece of equipment. If you buy a cheaper 200 amp class like off of Amazon, you can pretty much bet that you're going to hit thermal overload or the machine's going to shut down. Being completely honest with you guys, if your budget is at the 200 amp class machine, the most you can really expect to do any kind of volume with without a water cooler is going to be around an 1/8 inch or 3.2 millimeter material. If you go above that, you're just going to be disappointed, especially if you have ambitions on welding 1/4 inch or 6 mil plus material. You really need to be in a 250 amp class machine, not a 200 amp class machine. Well, with that said, let's talk about the settings that are available for AC TIG welding. Since we're welding on AC with a AC capable TIG welder, you need to understand what the AC wave is and why that's important. So depicted here is what is an AC wave. So older transformer-based TIG welders, this is what their output looks like. Modern inverters can often produce this kind of output, but a lot of them are what they call square wave. But for right now, let's just focus on this. This is an AC sine wave. It is called AC because it is alternating technically between positive and negative on the output. In the TIG arc, we see this as more or less you have a plate here, your TIG tungsten here. You will see on AC where electrons will jump off the plate in a wide cone back to the tungsten, and then you will also have a focused arc towards the plate. When you weld on pure DC with TIG, you only have a small arc cone. You do not have the wider arc cone of AC like with aluminum. Well, that is because we are more or less going through a sine wave of both positive and negative. This is depicting voltage. Virtually all older machines output on AC is a sine wave because they don't convert the sine wave from the wall outlet into anything special on the output. Modern inverter machines can often manipulate the output to whatever they want. It's very common with modern machines to have what's called square wave. All square wave is the output of the machine. This again is depicting voltage rather than being a rounded off profile, a sine wave, it is square. The benefit of having a machine, an AC TIG welder that can do square wave, is it affects how liquid the molten puddle is. So on pure sine wave, it tends to produce a more liquid flowing out weld. Now with square wave, where you have a fast, abrupt change positive to negative, it tends to make a less liquid weld pool in my experience. Now, another way to look at all of these waves, so like your machine might also have triangle wave where it looks something like this. Might be able to output triangle wave. This is heat input, okay? So anytime it's spending right here at the 0 volts, this would be 0, this is plus, this is minus, no heat is being input into the material. Therefore, the more time that you actually spend at positive or negative voltage, the more heat input is actually going into the material. So it's pretty easy to see that being tapered like this, because you don't have that flat spot, right here you're inputting less voltage than you are right here. So heat input wise tends to be higher with square wave than with sinusoidal wave, which that can be a benefit because with a 200 amp machine, you can often put more heat into thicker aluminum if you have square wave than you can with a sine wave like that. Now, when it comes to what wave should you use at what point, it's really pretty simple when you think of it. If you have super thin aluminum and you're having issues with square wave blowing holes through it, switching to like a triangle wave, if you have the ability to, may help you. Likewise, switching to a sinusoidal wave might also help you. Another thing to concern yourself with is noise. A lot of the newer machines can output a modified square wave where it tapers the edge of the wave to where it's not so abrupt and it's a lot quieter. A lot of people don't like the sound of AC TIG because it's that super high pitched, like annoying sound. Well, a lot of that comes from this, is that with that square wave, that abrupt voltage change produces that pitch. By changing it and doing a soft square wave, it can quiet the noise down significantly. Now, not all machines can do that, and it's mostly done just for a noise reduction. It doesn't really offer any performance increase other than noise reduction. Triangle wave tends to be very high pitched as well, and there's not much you can do about that. It is what it is, but like I said, heat input is going to be the least with triangle wave. It's typically going to be the most with square wave, and it's kind of going to be in the middle with the sinusoidal wave. So now let's talk about the very important control of AC balance. Is a typical balanced AC. This is 50-50, so it's 50% negative penetration, 50% positive cleaning action. This would be typical of a transformer machine that did not have adjustable AC balance. Fortunately, modern machines, you can adjust what the balance is, and effectively what you're doing is you're changing the ratio of how much time it spends positive to negative or negative to positive. All depends on how the machine labels this control. If you were to take this waveform and say that it's 1 second, then 50-50 means it spends half a second on negative, half a second on positive. If it's 1 second here, then it would be, this one would be 3/4 of a second on negative and 1/4 of a second on positive. So essentially, in a time frame of what they're referring to, it's just how much time is spent on the negative versus the positive. So when you look at here, you can see what's going on, because this is what the actual output of the machine, so your amperage, your voltage, everything. The output balanced here, this and this is the same, versus here you have much longer time that you're spending on a negative, which remember, negative is penetration, positive is cleaning, and a little bit of cleaning. This allows you to dial in the cleaning action that you need. The reason that's so important is if you run too much cleaning action, you more or less put more heat into your tungsten, which is not good. It's going to be harder for that to maintain any kind of resemblance to a solid. Not to mention, you lose penetration when you do 50% balance like this. You're going to lose your depth of penetration. So the more penetration you can get out of it, like with this, is going to be far more beneficial. The downside is if you use too little cleaning action and you're welding on dirty cast or something, you're going to have issues where you have bubbling porosity or overall a poor weld. Even surface wise, it might look clean, but internally, if you were to break it or cut it, you're going to find pores in it. And that's because you didn't boil out all of that via the cleaning action. Now, like I have written up here where it says a key to understanding waveforms is thinking of them as heat input. This is 100% true. If this negative side, which is depicted here as well, if negative is penetration, then this is how much heat you're putting on that, and this is how much heat you're putting on the cleaning action. So it doesn't matter if it's triangle, if it's sine wave, if it's square wave, that's just heat input. You need to understand that so when we start looking at pulse and a lot of other things, this all makes sense. So now that you understand the 50-50 balance and the 75-25, we're going to look at what's known as advanced AC. This is a feature that more modern machines have, so your higher end $2,000 plus machines. I haven't seen this as an option on many things under $2,000, but who knows, maybe you have one. But anyways, you understand the 50-50, 75-25. These are known as symmetrical AC. They're called symmetrical because the amperage on both sides, the negative and the positive, is equal. And no matter how you change the balance, which is the time it spends on positive or negative, you're not actually changing the amperage on the positive or negative. Now on the asymmetric AC, which some companies call independent AC amplitude adjustment, there's a lot of street terms for this, but we're going to call it asymmetric AC for this lesson. You're actually able to adjust the amperage on the negative to be higher than the positive. So like you could have 180 amps here and 50 amps down here, and it's asymmetric because it no longer is equal on both sides. So I know you're probably asking yourself, what is the purpose of this? And the answer is pretty simple. When you look at something like this 50-50 balance, so much of your heat is not really going towards any kind of useful production for the aluminum weld. Here, we might be putting the same amount of overall heat input into it as here, but we're shifting it to where more of that heat input is on the negative and less on the positive. because again, we don't really need that much heat input on the positive. We just need the positive to help us clean the aluminum, the oxide off, so that we don't have a dirty, filthy weld pool. Now, taking this theory a step further, there's also what's called independent waveform control. Most machines, as a matter of fact, all of the machines I have seen personally that can do asymmetric AC typically can do independent waveform adjustment. And what this is you could run like square wave on the negative, triangle wave on the positive, or vice versa. I don't know why you would do it that way, but this gives you more or less the ability to tailor the heat input and the amperage even more than this, the asymmetric AC, on the positive. So the benefit of what we're looking at here is just reduced heat input and more control over the cleaning action. I know this is probably pretty confusing, but the truth is that these independent waveform and asymmetric AC is just a way higher end TIG welders give you more control over dialing back the cleaning action. And the question is, well, why would you want to do that? Well, the truth is you got to remember that when you TIG weld on aluminum with AC, the whole purpose of the cleaning action is just to get you a clean puddle, to strip that surface oxide off. Well, once that surface oxide is stripped and the argon shielding is over that molten aluminum, you no longer have any kind of oxides forming due to reaction with oxygen. Therefore, you can get away with reducing your heat input via changing the wave on the positive or the amperage, and you'll still have a clean enough puddle to work with, but you can again put all of that heat input directly on the negative to get the most amount of penetration that is possible. You guys also have to remember that like pure helium on a DC TIG welder will have more penetration than any form of AC. And the reason is simple: 100% of the heat input is all on the negative. More or less what this is doing is giving you as close to DC performance as you can get while still maintaining cleaning action. And for the most part, you don't really need any of this. This is something that you can fool around with if you have a higher end TIG welder. It's mainly beneficial if you do a lot of production work of a certain thickness or certain part where you can literally dial everything in to get better penetration with less heat input. But for most things, this simply isn't really going to be a make it or break it. So now we're going to take a step back and talk about something that's a little bit easier to understand, and that's frequency control or frequency adjustment. So we're going to assume that we're just on a 50-50 AC balance here because that's kind of what's depicted, and we're on a sine wave for AC. Original transformer machines only had 60 hertz for an output because that was what was coming from the power plant on the input. So more or less when you hooked it to the wall outlet's frequency of AC carried through the whole machine all the way to its output. Therefore, in the past, everyone was limited to 60 hertz. Well, with the modern inverters that more or less create their own version of AC on the output, you can do all sorts of crazy things like change the frequency of the AC. And there's a lot of reasons why you might want to do it. So depicted here, I have 60 hertz, 120, and 400. Now 400 would have more squiggly lines than what's depicted here, but I did that so you guys get the picture. At 60 hertz, you produce a wide cone, an arc cone, and you produce very good penetration. At 120 hertz, it has a choking effect on the arc where the arc cone is not going to be as wide as 60. However, you are also going to lose a little bit of penetration. With 400 hertz, it's going to choke the arc down a little bit more than 120, and you're going to lose a little bit more penetration. Now, modern machines can go probably as high as 3,000 or 4,000 hertz, and honestly, beyond, 250, I don't tend to go any higher than that. Yeah, on some super thin aluminum on a critical joint, maybe 500-600 hertz, 400 hertz, something like that on repeatability might be the way to go. But in general fabrication, there really isn't a need to go above, in my opinion, about 240 hertz. I know you're probably wondering, well, why would 60 hertz have more penetration than 400, and it has to do with heat input. Every time that this sine wave or square wave or whatever wave you have crosses the center line, you have no output, more or less zero heat. Well, at 400 or even 120, you're crossing and hitting zero output far more than you are at 60, which is why if you're going to weld thick aluminum, like I would say 3/16 or maybe 1/4 inch and above, you're going to want to switch to a 60 hertz, or some machines can go as low as 40 hertz, maybe even lower. The lower the frequency, the more heat input time is actually spent heating the material, therefore the more penetration you're going to get. Likewise, if you're welding thinner material, jumping up to 120 to 400 will be a benefit because you're less likely to melt through because your heat input overall is less. Now, honestly, the choking effect on the arc above about 120, 240 hertz isn't really that significant. I've welded at like 1,000 hertz, and other than making a lot of noise, I don't really like it. Like, it doesn't really serve much of a purpose other than irritating your coworkers. Now, keep in mind, all of these frequencies here also can be done with asymmetric AC. They can be done with pulse. They can be done with different waveforms on the positive and negative, and they can also be done with different cleaning percentages or different AC balance. So now let's talk about DC pulse because it directly relates to AC pulse, and I need you guys to understand how pulse works. It's actually very simple. When you enable pulse on DC for, like, say, steel welding, you more or less set what's called a peak current, and you set a background or resting current. Because DC does not have positive like on an AC wave like depicted here, more or less you just set, say, your resting amperage at 100 amps, your peak amps at 200, and when it pulses, it is at 200. When it is resting, it is at 100. With most pulse programs, you can change how many times per second it pulses. So you could have like 33 times per second, or you could have it once every 2 or 3 seconds. So you can typically fully adjust that. And then you can also adjust the peak time. So like you see here on this waveform, the time it spends at peak, the more time you put on that, the less time is available for resting. So more or less it will spend more time at high output, less time at low output. The main benefit to pulse is you can typically achieve more penetration with less heat input because, again, on thinner material, the goal is to fully fuse it, but you don't want to put so much heat into it that you start melting through and make a hole. So pulse can really help with that. It can allow you to achieve things that you wouldn't normally be able to achieve, like full penetration with one pass on thinner material, without putting excessive heat into it. So it's pretty sweet in that respect. Well, now that you understand DC pulse, AC pulse works basically the same way. It's just that you're doing it with a sine wave or a square wave or a triangle wave. Here I have depicted a sine wave, but when you set your resting amperage on the pulse or your background current, that's going to be the low point when it's not pulsing, like depicted in this area. Then when it pulses, it's going to go up to your peak current that you set. It's just that because it's an AC wave here, a sinusoidal wave, you're actually pulsing a current that is in a way pulsing itself. I know that sounds confusing, but what you really need to look at this as is like an average heat input. So your heat input on this side would actually look something like this. Because yes, it has peaks and valleys, but the overall average heat input is going up and down. Same thing over here. Same deal. Now keep in mind that the heat input of the rising and falling current with the AC wave is playing a role, as is the actual pulse. So like this area right here where you're not pulsing, that's the average, and then the pulse brings the average up here, so more heat input. Pulse on AC tends to be something I don't recommend to people, and the reason's simple. If you remember in the first lesson in this series, I talked about hot shortness sensitivity of aluminum. Well, guess what? if you were to say set your pulse at 200 amps and your background current down here at like 40 amps, what would actually happen is you would induce hot shortness cracking into the material because you're bringing it up super hot, super fast, and then killing the heat, allowing it to cool very fast. And once that molten puddle were to dry up, you'd more or less have instantaneous cracks in it. So doing pulse on aluminum, I generally don't recommend it. And if you're going to do it, you want to keep the background current high. It's very common on TIG with DC to run 100, 150 amps on the high side and then say 30, 40 on the low, and you're not going to get cracking issues with that. On aluminum, you don't really want any more difference than maybe 20% from high to low, or you will risk getting cracks. And I'll even shoot a video demonstrating that in the future. Now let's go into some real welding nerd type stuff, and that's where advanced AC pulse can come into play. Now, this is a term that was coined by, I believe, Everlast welders, but it's done on other machines besides theirs, and it's kind of an interesting concept. So take what you've learned so far in this video and apply to what we're talking here. What advanced AC pulse does is it allows you to dial a ton of amperage on the negative side and nothing on the positive. So if you look at this waveform here, this is depicting your normal sine wave, or you could make it a square wave, whatever. And then when the pulse hits, the pulse only hits on the negative side of the wave, aka the penetration side of the AC. And then when it comes back over, there is not amperage or heat input on the positive, the cleaning action. Most machines will not allow more power output than the rated output of the machine on the negative. So if you have, say, a 200 amp machine, it's not like you can pulse at 230 amps on the negative. However, some machines for a very short time will actually more or less output more amperage than the faceplate rating on this pulse in order to try and gain more penetration. And some machines for the pulse on time will more or less eliminate all of the positive wave for a microsecond or very short amount of time, and it will just keep the negative going and then hop off a pulse and let it do the cleaning action where it's hitting the positive. So machines that can do that can gain huge penetration on thicker aluminum. Like you can start seeing like 350 amp machine performance when it pulses for how much penetration you can get. Because again, the whole goal with AC is to get enough cleaning action to clean up that molten pool. But once you have it established, shielded in argon, blasting it, I don't know, once every second and a half with a whole bunch of DC current, like an extended length pulse, can get you a lot more penetration and not really give you a filthy weld pool either. I believe Everlast welders do it this way, and they actually fix the pulse when you enable this. I think it's like 1.5 for every 2 seconds. It doesn't allow you to do it fast because then you would have a dirty weld pool. So it's set at a point where they tried it out and were able to achieve more penetration without muddying up the puddle. I've heard this works really good. Not all machines that have advanced AC can do it this way. That's something where you're going to really have to read the manual of the welder you own or a welder you want to buy to understand how their advanced AC pulse works. But this is how Everlast and some of the higher end ones do it. Also with advanced AC pulse, you can typically use different waveforms on both the positive and negative still. So just like depicted here, square wave on the negative, triangle on the positive. All of these controls typically are active even under pulse. So it's pretty amazing what you can do with all of these waveforms. Now I know all of this is an absolute ridiculous amount of information, and hopefully I haven't lost you yet. But again, let's just go back to what I've said so many times in this video. Just look at all of this as heat input. When you look at this, okay, we have a little bit of heat input. Now we're going to positive, little bit of heat input, and then a whole lot of heat input, and then we go back. That's when you look at it like this all makes sense. This isn't hard to understand. Just look at it as heat input. So to help you guys kind of remember what we covered in this video, I wrote this out and we're going to read it together. I want you to read this information in your head, so hopefully you remember it. I know that it took me a while to remember all this junk. So sine wave for a setting on a machine, which is all older transformers and many modern machines can also do sine wave, but sine wave produces a wetter puddle and medium heat input. So if you don't want to blow holes through thinner stuff and you want a quieter arc, because this is probably the quietest of all the arcs, pick a sine wave. It works great. It's worked for 50, 60, 70, 80 years without many issues. And it just flat out is a good way to go for a lot of stuff. But wet puddle, medium heat. Triangle wave produces a drier puddle, so it's not as wet, and it puts the least amount of heat input. Triangle wave should be used on thinner material only. You do not want to use this on thicker material. You will produce typically a lack of fusion issues. Remember, aluminum is probably the best masker of poor welds you will ever find. You can make welds that look super hot, that are perfect looking, and then you cut it and etch it. Most of the time you don't even need to etch it, and it'll be the worst fusing weld you've ever seen in your life. So triangle wave, thinner material. Square wave, if you can adjust it and put that on, produces, again, drier puddle, and it has the highest heat input because the time that you spend at that negative, that penetration, is just 100% amperage output. It doesn't vary. Therefore, per second, your heat input is higher. Square wave is what you should be using on anything requiring high heat input. It also does work effective on thinner material, probably better than sine wave because the amperage drop off is so fast that the puddle tends to be less liquid, less melt through. So square wave is honestly the most versatile, and that's what I tend to use the most. Unless I'm welding absolutely thin material, I do not use triangle wave. Now for AC balance, what you need to remember is for most machines in North America, 65% to 80% negative is where your starting point should be. So your AC balance should be in this ballpark. I would say start at 70. Now if your machine adjusts the positive side and not the negative side, you need to adjust your machine between 20 and 35%. The easiest way to know if your machine is opposite is that if you set the machine for 70%, you strike an arc and a tungsten melts off, you probably need to set it at 20 to 35%. One of these two settings is where you need to be. Once you're able to achieve a clean puddle, you're probably going to leave it where it is and not adjust it that much unless you really do some dirty aluminum welding. So I generally stick 70, 75%, especially for newer aluminum. Frequency. The lower the frequency, the more penetration. 60 hertz is what you should run on thicker aluminum. If you have the ability to adjust it lower, like my Miller Dynasty and my Fronius can go below 60 hertz, thicker material, I would generally recommend it. Your heat input will be higher per second with a lower frequency. Now for thinner material, you can experiment. 120 to 240 hertz generally works pretty good on thin. Higher than that, it becomes annoying, and there's not really much benefit. Also, and I didn't mention this earlier, you get less arc wandering in corners, like on a fillet weld, if you run higher frequencies. So if you're having issues where the weld is just getting super wide and the arc's wandering a lot at 60 hertz, try upping it to 120 and see if it works better for you. You know, it really pays to experiment with this and get a feel for what your machine does, because I'm not joking. I've welded with probably 30 AC TIG welders, and every one of them, the arc worked different. It's the nature of aluminum welding. All right, let's go to conclusion. So I know I covered a metric ass ton of information in this video, and maybe it still doesn't make any sense to you, and that's what the comments are for. So if you got any comments or questions or thoughts or opinions on what you saw here today, feel free to leave them and I will get back to you. With that said, I hope that you guys understand a lot more about what's going on with the settings with AC TIG, and moving forward when we're actually going to do TIG welding in this video series, this will really, I mean, I can't overstate how much this information will help you. at understanding what's going on, and you'll be able to make better adjustments and get your TIG welding to work properly on aluminum. I have talked to a ton of people over the years that tell me, like, I can't get the AC TIG welding to work right. And then I ask them to send me a picture of their welder with the settings or tell me what settings are running, and everything is all wrong. And once they get things dialed in to where they are, where they should be, things start to make sense and work. And that's the key takeaway, is that you really have a lot of range in settings with aluminum, but at the same time, they have to be kind of in a general area for things to work. And rarely are you going to achieve better results screwing around with settings and putting things at the maximums, or at least that's my opinion, I guess, and I'm going to stick to it. With that said, hopefully you enjoyed the video. Hopefully you learned something. Until next time.